A lathe is just one of several machines used for cutting materials. While cutting, the machine uses power, in this case, electrical power. On this lathe, a meter shows just how much power is being used. It's measured in kilowatts. Now, one factor that can affect the power is the shape or geometry of the tool. This is a knife-edge tool. It has a clearance angle of about 6 degrees and a rake angle of about 15 degrees. Let's find out what happens if the geometry of the tool is changed. Here we have 4 knife-edge tools, each with a different rake angle. Their clearance angles are all the same. For this experiment, we'll use this specially prepared piece of mild steel. We've taken a core from the middle to make it easier to film. First, we'll try the tool with a 10-degree rake angle. The tool must be carefully positioned and properly restrained. Before cutting begins, the lathe will use some power for turning the work round, and even more power is used when cutting starts. The total, 2.6 kilowatts. Next, we'll try a rake angle of 20 degrees. Same speed, same feed. And the total power used, 2.3 kilowatts. Now a rake angle of 30 degrees. Same speed, and again, same feed. And even less power is needed. Finally, a rake angle of 40 degrees. This time, the power used is, well, what do you think it is? Less still, 2 kilowatts exactly. Let's put these results on a chart. For 10 degrees rake, the total power used was 2.6 kilowatts. For 20 degrees, 2.3 kilowatts. For 30 degrees, 2.1 kilowatts. And for 40, 2. But for each test, the lathe was using some power before the cut began. To get the power used in cutting the material, we must subtract this from the total power. So, the larger the rake angle, the less power is used. Now, this must be related in some way to the shape and cutting action of these tools. As with most cutting tools, the material is sheared along a plane at 90 degrees to the face of the tool, the shear plane. The length of this plane, that's this distance, is determined by the rake angle of the tool. Here, the rake angle is 20 degrees. The larger the rake angle, the shorter the plane. The smaller the rake angle, the longer the plane. Let's compare the length of this plane with the power used. Can you see what's happening? The power seems to depend on the shear plane length. The shorter it is, the less power is used. By giving a cutting tool a really large rake angle, there'll be a very short shear plane and little power will be used. But just how serviceable is a tool like this? After only a few moments' use, the cutting edge is damaged. Damage like this is expensive, so is excessive power consumption. So this business of choosing the right angle is very important. From these results, a tool with a rake angle of between 10 degrees and 20 degrees, say 15, would be the most suitable. But that's for one material. Free-cutting, mild steel. There are other materials such as brass, aluminium, and nylon. Would, say, 15 degrees be the right rake angle for cutting any of those materials?